So, programmable cryptography is an evolution of cryptography as we know it today. And we can say that cryptography as it is today is known as special purpose cryptography. So, the thing with programmable cryptography is that it provides the building blocks to create systems where sensitive data can be used in computations without being exposed. So, along the lines of performing computations or calculations on encrypted data. So it extends cryptography beyond the simple encryption and decryption or signing and verification to support custom computation logic within that context of privacy. So some good examples is performing some computations or calculations on encrypted data. You could encrypt some values, maybe like one and two, and then perform some addition while they're still encrypted without having to reveal these values. Or you can prove some complex statements about some secret information without having to reveal that secret information. So traditional cryptography had a focus on securing data while it's being exchanged or when it's in storage. So for example, when you're getting some information from a web server, then there's some encryption that happens and decryption between the client and the server. Or think of passwords being stored in a database, they have to be hashed. So that's what traditionally cryptography has been used for. And it uses some fixed primitives that are designed for security, maybe to achieve stuff like the confidentiality of information or integrity, stuff like symmetric encryption, which uses a single key for encryption and decryption of data. And an example of this is the Advanced Encryption Standard, AES. Then we have asymmetric encryption, or what is known as public key encryption, that employs a pair of keys, one for encryption and one for decryption. And a good example of this is RSA, or elliptic curve cryptography. So typically, the goal of symmetric and asymmetric encryption is to achieve confidentiality of information. Only the people who have the keys, whether it's a single key for symmetric or the decryption key for asymmetric, can access the information. Then we also have hash functions, which produce a fixed size string of characters, which we can say is like a fingerprint of data. So once you pass once you pass some data to a hash function, you will get a a string of characters that's of fixed length, and it represents that data. And any change you make to your data will reflect in the resulting hash. So what hash functions typically do is protect the integrity of information, and you can be able to notice any tampering that is done. And a very popular example of hash functions is SHA-256. Then we have digital signatures, which kind of combine asymmetric encryption and hash functions to verify the authenticity and integrity of a message. So another thing about programmable cryptography is that you can achieve fine-grained privacy in that you can reveal only parts of some information, or you can prove partial knowledge of some information without revealing that data or that information itself. And this is actually an advancement from how we know cryptography right now, where it's like if I encrypt some data, then only the person who has access to decrypting it can decrypt it, but then they have access to all the information, not just some parts of it, if I would like to only reveal some parts of it. So some major technologies that fall under programmable cryptography, there are many, there are several, and they're actually, you come to realize these are technologies that people have been working on these technologies for years, but right now is when people are starting to see a programmatic breakthrough in implementing all these concepts. So conceptually, they've been around for a while, but people have just been tinkering with it and trying to implement them. So I'll be focusing on only three of these, and that's zero knowledge proofs, multi-party computation, and fully homomorphic encryption. So starting off with zero knowledge proofs. So zero knowledge proofs are a cryptographic protocol that allow one party to prove knowledge of some certain information or that a computation was performed correctly without having to reveal that information. And it involves two parties, in zero knowledge proofs, there's a prover and a verifier. And just like the name suggests, the prover is the one who's trying to convince the verifier that they have some certain knowledge of information without having to reveal that information to the verifier. So actually, while I was reading about zero knowledge proofs, I realized that the very first introduction of the concept of zero knowledge proofs can be traced back to the mid 1980s in a paper called The Knowledge Complexity of Interactive Proof Systems. I will link that paper in the description. And you can see how long people have been working on these things. And at a high level, how zero knowledge proofs work is that a verifier asks the prover to perform a bunch of tasks that only a person with that knowledge can be able to perform. So if they actually don't know this information, then they will eventually fail at these tasks. So the more the verifier asks the prover to perform these tasks, the easier it is, or rather the lower the probability for the prover to lie about having some knowledge. Zero knowledge proofs can either be interactive or non-interactive. Interactive, whereby the prover and the verifier have to interact. So the prover has to provide the proof to the verifier, and then the verifier could ask, perform a certain action, and then it goes back and forth. And they'll have to do this with every verifier that they come across. But it could also be non-interactive, whereby a prover just generates a proof and anybody can verify the information or the knowledge of the information just based on that proof. So the programmable aspect of zero knowledge proofs is that you can define any circuits that align with whatever you want to prove. So it doesn't just have to be knowledge of information. Remember, we also said you can prove that a certain computation has been performed correctly. So that's a circuit on its own, and then another circuit on its own that proves maybe that you know what the values, maybe value A and value B, are without having to reveal that information. So there are actually three characteristics that are key to zero knowledge proofs. There's completeness, soundness, and zero knowledge. So with completeness, it's that if a statement is true, then an honest verifier can be convinced by an honest prover that they possess this knowledge and that that statement is true. So if a prover is trying to prove a statement is true, then an honest verifier can be convinced because the statement is true. With soundness is that if the statement is false, then a dishonest prover can never convince an honest verifier that the statement is true or that they possess this knowledge. Then with zero knowledge, as the name suggests, there's no more information that will be learnt by the verifier other than just that the statement is true. That's it. There are different kinds of zero knowledge proofs. There are ZK snarks, ZK stacks, and bullet proofs. So ZK snarks, the snarks in ZK snarks stands for succinct non-interactive arguments of knowledge. And ZK snarks are known for their efficiency. They're actually really preferred because they provide really small proofs in terms of size, which results in fast verification times, regardless of how complex the proof or the statement being proven is. A key feature of ZK snarks is the trusted setup phase. So initially, there is a trusted setup phase where a set of parameters are generated, and this trusted setup phase usually uses a secret. But if this secret is exposed, it will compromise the security of any proof that will be generated subsequently in that setup. So that's a security concern that most people have with regards to ZK snarks. So ZK snarks also use elliptic curve cryptography for verification, whereby the verifier has to perform pairings on the elliptic curve. And that means that this scheme relies on the discrete logarithm problem, which means if our secret prime number is a really, really big prime number, they're safe from attacks by the computers that we currently have, even if it's a supercomputer. But they're still quite susceptible to quantum attacks because quantum computers can solve the discrete logarithm problem. Then we have ZK stacks. The stacks in ZK stacks stands for scalable transparent arguments of knowledge. The key feature of ZK stocks is that there's no trusted setup phase that is required. ZK stocks use hash functions instead of elliptic curve cryptography and publicly known randomness to generate proofs. So the fact that they use hash functions, and a popular example, as we mentioned, is SHA-256, means that they're quite resistant to quantum attacks. And also because there's no trusted setup phase, then there is no secret that we're using that can compromise the security of ZK stocks. There are actually some real life implementations of zero knowledge proofs, not just in blockchain, but even in other areas in major tech. So, for example, think about Starknet in blockchain. Starknet is a layer 2 blockchain on Ethereum, and they implement ZK stocks to scale Ethereum by processing the transactions off chain and then verifying their validity on the Ethereum mainnet. So, how Starknet works is that they batch transactions and then generate a ZK stock proof. And then that proof will be submitted to Ethereum's layer 1. And in the layer 1, it will be verified, of course, very quickly because it's just a single proof that's standing in for a bunch of transactions. It will be verified by the nodes on the chain. And the proof attests to the validity of all the transactions that have been batched in that proof. So, if you're familiar with the blockchain trilemma, then you know that one of the challenges that Ethereum faces is scalability. Because the more decentralized and secure the network is, then the less scalable it is. So with implementations like this, where we're using zero knowledge proofs to attest to the validity of transactions without them having to go through each node on the chain, then we are able to solve the scalability issue that affects Ethereum. But beyond even blockchain, there are several companies or institutions that have implemented zero knowledge proofs. Actually, quite recently, Google revealed that they have integrated zero knowledge proofs into their Google Wallet platform, and they aim to enhance digital identity verification. So users can be able to prove specific attributes like their age without having to disclose any sensitive personal information. For example, if you have to verify your age, that you're above 18, you might be required to submit your identification card. And most people are not comfortable with, sharing the identification card because it has some personal information. So with zero knowledge proofs implemented in this manner, you can be able to prove that yes, I am above 18, but no more personal information on the identification card will be revealed. They have revealed that they have plans to open source their code so that they can be used by other wallets, but currently their code is not open source. Then we have Microsoft, which has implemented Spartan, a high-speed ZK snack that doesn't require the trusted setup phase. So as we talked about, the trusted setup phase uses a secret, which basically makes the security of the entire scheme quite weak. Because if it's revealed, then the proofs generated after that will not be valid, will be affected by that. But with Spartan, they have implemented a ZK snack that doesn't require the trusted setup phase. Some of the distinctive features of Spartan that they've implemented is not toxic waste, meaning that there's no need for a secret that is being used. Spartan is a transparent ZK snack and does not require a trusted setup, so it does not involve any trapdoors that must be kept secret or require a multi-party ceremony to produce public parameters. They have a paper on that, and also it's on their GitHub, with the most recent update being on 24th of May 2025. So they're still working on it. Then we have TikTok. TikTok has also implemented ZK snacks into a trustless attestation verification system that they have. So for them, they're focusing on trusted execution environments. And in the case of TEEs, as they are known, is that relying parties need to verify that the TEE is in proper condition before they use it. So there's some attestation that will be generated and provided to the relying parties, but then this requires the relying parties to trust the attestation service. But by relying on zero knowledge proofs, the attestation service can demonstrate to the relying parties that the attestation process was correctly executed and that whatever attestation is provided to them is valid. And by doing this, they're able to ensure the integrity of that process and reduce the trust that is required by the relying parties. So they've also shared these updates on a blog, and the code is also on GitHub, with the most recent commit being on 12th March 2025. The blog was published on 3rd January 2025. So I guess we can see how zero knowledge proofs are being utilized in all areas, and not just necessary in blockchain, but also in all areas. As long as you're dealing with any data, you can benefit from using zero knowledge proofs. So now let's move on to multi-party computation. And multi-party computation is a cryptographic protocol that lets multiple parties jointly compute a function over their private inputs without revealing these inputs to each other. So it builds upon the Shamir secret sharing scheme, which is an algorithm where a private key is divided into shares, and then these shares are distributed to different parties so that each party possesses only a part of the secret, but no one has the entire secret. And in order to reconstruct the original secret, one would need a minimum number of shares. So depending on how you implement the Shamir secret sharing scheme, it could be you have the freedom to specify the minimum number of shares that would be required to reconstruct the original secret. So the thing about this scheme is that computations can still take place on the shares, and the output of these computations will still be correct, but nobody has access to the entire secret. Nobody has access to each other's secrets. So we have an image from ZK Illustrated that kind of shows how this works, and we can look at how it works. So if we have a secret key 42, we can put it on a graph at point 042, and then we get 4 points on this line, and we share them out. We distribute them out to 4 people, and the minimum number of secrets needed to reconstruct the original, or the minimum number of shares, is 2 in this case. So if 2 of these parties come together to recalculate the original secret, that, let's say if it's a key, we want to use the key for decryption, then a minimum of 2 participants need to be present for that key to be used. So here we can see that we're calculating the slope from these 2 points, 152 and 372, in order to get the y-intercept, and the y-intercept is going to be 42, which is the secret key. But any individual who wants to reconstruct the original secret just based on their point would be unable to do so. So the point of multi-party computation is to allow different parties to use a protocol that protects their data during collaborative computations. So let's see the example of maybe you want to calculate Nasi's average salary, and you have 3 Nasis with you, and neither of them want to reveal how much they earn. So what could happen is each nurse could break down their salary into 3 figures, unequal figures, and then keep one share and give another share to the other person and another share to the other person, and the other nurses would do the same. So now all these values can be put together to calculate the average, but nobody will know how much each nurse earns, because nobody has every share that will be needed to reconstruct a particular nurse's salary. Another good example of how multi-party computation is used is when it comes to companies that want to do collaborative analytics in terms of their business. So maybe they have some information on their customers, and they would love to perform some analysis on their customer base. Different companies that our competitors can bring their data together, use it for analysis, and then at the end of the day, no other company has access to your private information that you are using. So another application, major application of multi-party computation is the TLS notary, which builds upon TLS, transport layer security. So TLS is the cryptographic protocol that handles encryption of data while it's being exchanged between a web application, which we can refer to as the client, and a web server, which we can just refer to as a server. And a TLS connection is initiated using a TLS handshake, whereby the client authenticates the identity of the server using a digital certificate that's provided by the server. And then both of them generate a session key that will be used for symmetric encryption going forward of all data that is exchanged between the two. However, the problem with this is that communication is only private and verifiable by the server and the client. So in a case where you want to prove that the information that I'm using, or maybe a document that I obtained from a particular server is legit, you would need to prove that, but it would be very difficult to prove such a situation. So how TLSN or TLS Notary solves this is by introducing a third party called a verifier, which basically functions like a notary. So going forward, the term client refers to both the application, which can be called the prover, and the notary, which we can call the verifier. So now there's the client made up of both of these, and then the server, which is still the web server. So the prover initiates the TLS handshake and physically communicates with the server, but during the generation of the session key, the prover and the verifier will compute separate shares of the key. And whenever the application wants to decrypt a message that has been sent by the server, it has to perform this along with the verifier. So both the application and the notary are bringing together their secret shares of the key, of the session key, and then it's used for decryption. On the surface level, the TLSN will, or the TLS handshake takes place exactly as you would expect it to take place, exactly as it is right now. There is no indicator of a third party being there, that is a verifier. But under the hood, the verifier is contributing their share for decryption of the message, but does not participate in any more than that. So generally, that's what multi-party computation is all about. It's just having multiple parties bring together their secret data, and then they combine it and use it for computation, but nobody knows the actual secret. All these shares make up a secret, but none of them have the entire secret, and they can compute functions using these inputs without revealing their secret shares to the other parties. So now let's move to fully homomorphic encryption. And generally, homomorphic encryption enables secure computational operations on already encrypted data. So if you have some data, you can outsource it to a third party while it's encrypted, and they can perform some function on it, on this encrypted data, get a result, and the result will also be encrypted, and then they will share that result with you. And once you decrypt this result, it will be the same result you would have gotten from performing that function on the unencrypted inputs. There are three common types of homomorphic encryption. There is partial homomorphic encryption, somewhat homomorphic encryption, and fully homomorphic encryption. So with partial homomorphic encryption, you can only perform one type of operation on encrypted data. So it's either just addition or just multiplication. You cannot perform addition and multiplication on the encrypted data. It's just one type of operation that can be performed on the encrypted data. The reason we're talking about addition and multiplication operations is because they allow us to replicate binary circuits like AND or XOR kind of circuits. And then with somewhat homomorphic encryption, you can perform more than one type of operation on encrypted data, so addition and multiplication, but there is a limit on the number of operations that you can perform on the encrypted data. And this is because of a concept known as noise. And in this case, noise is just a small random value that is added to the data during encryption. So by adding noise to our data before encrypting it, the security of the scheme is dependent on the approximate GCD problem. So a malicious party cannot use the Euclidean algorithm to calculate the secret key, because there is a secret key that is used in encryption, a prime number P. But if we add a random value, which is the noise, to our data before encrypting it, it is difficult to use the Euclidean algorithm to arrive at the secret key that is being used in the scheme. However, the problem with having noise in our ciphertexts, the encrypted data, is that each time a multiplication operation is performed on the encrypted data, the noise grows. And it could grow to a point where it is larger than the secret key, the prime number, which is the secret key. And what that means is that it's difficult to extract the plain text result from the ciphertext result, because the private key and the noise have clashed. Actually, this is why somewhat homomorphic encryption has limits on the number of operations that can be performed on the encrypted data. It's so that we can control the growth of the noise so that it doesn't become overwhelming to a point where we cannot extract our result. So there are a few methods that have been introduced to deal with this noise and the growth of this noise, to reduce that chance of losing our result from the ciphertext, our plain text result from the ciphertext result. And these are what form the basis of fully homomorphic encryption. So with fully homomorphic encryption, you can perform any type of operations on encrypted data, and there is no limit to the number of operations that can be performed. This is because there are ways to handle the growth of the noise. So the first ever fully homomorphic encryption was created in 2009 by Craig Gentry, and there is a paper on that, which I will also link. But that was the very first creation of fully homomorphic encryption. And in that paper, he proposes a way to deal with the noise so that we can perform multiple operations on the data. And this method is known as bootstrapping. And Vitalik talks about this in one of his blogs that he wrote in 2020, and he goes into detail about it. And he also talks about other methods to deal with noise and noise growth, like using matrices. So if you would like to dive deeper into that, then you can check out his paper, which I will also link in the description. So that's a simple introduction to fully homomorphic encryption, and actually generally just a simple introduction to programmable cryptography, zero knowledge proofs, multi-party computation, and fully homomorphic encryption. So another note that I would love to make is, since we have seen that ZK snarks are quite prevalent, there's the Microsoft ZK snark implementation. TikTok's attestation verification system uses ZK snarks. A good material to use if you want to familiarize yourself with the underlying foundational concepts of ZK snarks, and all the way up to hardware description languages like SACOM. A good resource would be the Moon Math Manual by Least Authority, and you can download it from the GitHub, the latest version. I think with that, I've just built a strong case on why everybody in technology needs to be paying attention to programmable cryptography, because the thing about programmable cryptography is it's about preserving the privacy of the data that is being used on the internet. And since we're all using data, we're all exchanging data on the internet, then of course there's a need to preserve the privacy of our information. We know that whoever holds the information has the most power. So these technologies can benefit any industry, whether it's even machine learning, training AI models, big data analytics, everywhere. blockchain, of course. And the only reason why these technologies are quite prevalent in blockchain is because it aligns with one of the ethos of blockchain, which is to be able to control our data, who has access to it, what can it be used for, and these technologies offer that privacy when it comes to our data. When we're explaining Web 1, Web 2, Web 3 to people, we say Web 3 is read, write, and own our own data and control what can be done with it. So with these cryptographic technologies or advancements, we can achieve that. So everyone should be paying attention.